In this lecture, I want to give you a better feeling of what the continuous distributions, the uniform distributions, and the normal distributions are about, and to reinforce some things that we've already seen. I'm going to start here. We're going to import pandas, import numpy, import scipy.stats, and we're going to call it stats. I'm going to draw some graphs, so I'm going to put percentage sign plotlib inline. I'm going to be creating some populations, so I've set my population size 1,000,000 using these underscores as notation to help us read the number. Have a sample size of 1,000 because I'm going to take some samples. And so those in general. Now, in particular, I'm going to be setting up a population of data that's uniformly distributed. So X twiddle U A B. So I've set up my A as 50 and my B as 100. And I set my population to here. It's in the population is np.random.uniform, and beginning at A and ending at B, and with the population size. And so when you use this, you may well want to put the literal numbers in there rather than the variables. I am putting in the variables here for pedagogical purposes to reinforce the notation from the last lesson. However, also frequently in programming, it's nice to have things set up in concepts, because just as it makes it easier to understand in teaching, it makes it easier for someone else to read your code. I'm taking my population data, I'm putting it in a data frame, again making a data frame from a dictionary, and in this case just a one-entry dictionary. And as my last step, I want to do a histogram of this so you can see how the data is distributed. And so I shift and enter, and there's my histogram, and you can see, yes, it goes from 50 to 100. There's all my data, and there's a little wavy along the top because it is randomly generated data. But we have a population size of 1,000,000, so when you have a big population, it tends to fill in your distribution rather fully. In this next, where we have our going to calculate our mean, a plus b over 2, calculate our variance. I'm going to call it sigma 2 as opposed to var, because our sigma is our standard deviation, and so sigma squared is our variance. And then I'll print out what that is. And so for this population, I have my my mean is exactly this from our calculation, and or for the uniform distribution, and our variance is exactly this. In the next, I want to take the actual data and calculate the mean and the variance from it. Okay, so I've got my popdf population dot mean, comma, popdf population standard deviation squared. Shift, enter, and so notice that the mean and the variance of this are almost exactly what the theory predicts. That's because we have a population of 1,000,000. Okay. Now, from this population, I'm going to take a sample. Okay. Sample size, recall, is 1,000. It's a big size sample. Going to roll that into a data frame and calculate its mean and standard deviation. Shift enter. And so, okay, so we have our sample here has a mean of 74.8. Well, that's not quite 75. It's a bit farther from the ideal prediction than dead on, but it's still pretty close because these are estimators, and 1,000 is a big sample size. The variance is also close. There's a little bit more difference in the variance here. Okay. Now, this next, my hope is to demonstrate to you what probability of an event means. Okay. I'm interested here in calculating the probability of a student getting a C if this is my grade distribution. I set it up from 50 to 100. If that is my grade distribution, what would the probability of getting a C be? Well, a C in my course is between 80 and 70. So I have my stats.uniform will give me a means to do that. This in the stats, the SciPy has a different notation for it. They start out with the lowest point, okay, for your uniform distribution. In this case, it's 50. So you put log equal 50, and then the scale is the width of the distribution, which is also 50. So from 50 to 100, we set it up like this. It's different from the NumPy notation, and potentially to be confusing. So you just have to know where you are. And the .cdf, this is your cumulative distribution of frequency. And so we take the top value of 80. So this number by itself gives us all the probability up to 80. And the second one is exactly the same except for the 70 here. It gives us all the probability up to 70. So we subtract the probability up to 70 from the probability up to 80. Okay, shift enter, and this gives us what the probability of getting a C is, which it's a point, well, it looks like a 0.2, right? 0.19999, okay. So if I take this probability times my sample size, this is how many in my sample I would expect to get a C. So out of the 1,000, I expect about 20% of them to get a C, and this is about 200. Okay. Now, but what about my actual sample? Okay, how does that? This is a theoretical prediction. This right here, this 200 is a theoretical prediction. How did my sample actually turn out? Well, I look at I set up a mask, my C mask to C. And so in this first one, I say, okay, which in my sample had a score less than 80? Okay, and the second one, I said, which in my sample had a score greater than or equal to 70? And I say, this and thing, what's both of those happening at the same time? So both of these at the same time are what are in my mask. And as you recall, the mask consists of a series of values that are just true or false, 1 or 0. When I do a sum of this, it adds them up like ones and zeros, and so it gives me the number that I have, and 209. So 200 isn't the actual number isn't too far from the prediction. This is a pretty good estimate. And when we talk about the central limit theorem and confidence intervals, etc., we'll learn more about why that is true, or at least a better calculational sense of it. Now I want to try this same stuff with normally distributed data. And so I will, instead of a population, I'll have a normal population. I'll do np.random again, but this time instead of .uniform, I'll do .normal and put in my mean of 75 and a standard deviation of 10 with the same population size. As before, I'm going to make a data frame out of it, calling the data population data, but I'll call the data frame in pop for normal pop. And then I'm going to calculate its mean and its standard deviation. And again, this is almost 75. This is almost 10. So our population does have close to what I had desired it to. Let's see how this is distributed. I'm going to plot a histogram. I'm going to set the number of bins being equal to 12 to show you how it curves. And so, yeah, my population data curves like a bell curve. It looks, I had wanted it to be normally distributed, and it is in fact normally distributed. This is what they look like when you find them in the wild. Okay. Now I'm gonna, as before, I'm taking a sample from this of sample size 1000. Okay, putting it into its own data frame. Okay, and then with this one, I'm going to calculate the probability of getting a C. Call this n prob of C, because n for normal. And again, we're calculating the CDF here, so the cumulative distribution of the probability of a normal distribution, NORM, the SciPy calls it. Mean of 75, standard deviation of 10, so the cumulative distribution up to 80, and then subtracting from it the cumulative distribution up to 70. And this right here is the number I expect to be in that sample. This is the theoretical expectation, calculating the probability. Okay. And then, okay, so that's the theoretical expectation. What is the actual number? Okay. Well, I again make my mask, my normal C mask from my normal sample, the ones less than 80, and then the ones greater than or equal to 70, and then the sums of sum of all the ones that make it through. And I got 385, so not dead on the same as 382.9, but pretty close. Now, okay, how many of these, okay, got an A, okay, by making a score of 90 or more, okay. Well, so I define my mask there to count as true the number that are greater than 90. Then I take a sum of that. Okay, so I actually got 62. Okay, how many would I have expected? Okay, well here I calculate the probability of A by, well, so 1 is the probability of anything happening, and right here, this cumulative probability, this is the probability of getting up to 90. I calculate that probability, multiply it times the sample size, and it's about 66, 67. So the actual value isn't too far away from what the theory predicts. It's not exact. We would be suspicious if it were. And when we get into the central limit theorem, we will learn more about that.